Today we're going to take a look at something called optimization. And one of the issues overall with optimization is that it can feel like the problems are all very different. But they all boil down to doing the same types of things when you get right down to solving the problem. Now, one of the things that I want you to be aware of with optimization is that while I've got sort of like 5 steps listed, there's nothing about these 5 steps that says this is the order you need to go in, these are all the details, you have to write this down on every problem. It's not quite like when we did curve sketching, where we said we're going to have to fill in all these details to get all these details onto a graph. It's not like that, okay? So the first thing is often, not always, but often it's helpful to have a visual of what's going on, a picture. Maybe that looks like an actual equation, a graph. Maybe it looks like a sketch of an actual physical object. Maybe it means making a table, so some kind of a visual. The second thing to recognize is what you know and what you need to find. And I know that just sort of seems like a basic problem-solving thing, but sometimes it means labeling pieces of a picture. Sometimes it means just in your mind thinking through what do I know and what pieces am I looking for. The third step is probably one you're going to write down. You're going to figure out what equation it's going to be to solve something. So, for instance, let's say you had a problem where you're asked to find something about area. And it's an area of a rectangle. Do you guys remember what the area of a rectangle is? What? I'm sorry, I'm hearing 2 things. What am I hearing? Length times width. We'll call it width, but yeah, you could use the word height if you want. Length times width. And if you aren't careful, the length and the width, again, if you aren't given enough information, could be 2 different variables, right? They could be 2 different things you don't know. Well, the reality is that the information you're given will always allow you to take whatever it is you're trying to work with and simplify so that it only has 1 variable. So either you'll be able to write the length in terms of the width or the width in terms of the length. Okay? So that's part of this thing too, where it says write that equation in terms of only 1 variable. And then you're going to determine the maximum and minimum values of, if there are any, of the variable that you're using. And you do that using calculus. Okay, so finding maximums and minimums means doing what? Taking derivatives and setting them equal to 0, solving them, right? So the last step of all of this is going to be the calculus step that you now have. Now, you've seen some of these types of problems before, and you've used different methods to solve them. So the first one is not anything new. You've probably seen this particular problem or something very, very similar to it in an algebra course. But it's the one we're going to start with so I can show you how this process works. It says a 3-sided fence is to be built next to a straight section of river. Now, if you don't like the river, we can pretend like it's being built next to a barn, so it's actually enclosed in something, which I kind of like a little bit better. I'm not sure why you would build a fence beside a river. But that said, maybe it's a garden. I don't know. But still, that doesn't make sense to me. Why would you even need a garden fence? But okay, so we got a fence next to a river. So the first thing that I'm looking at this as I'm sort of thinking through it is I'm like, I've got a picture in my head of what's already going on. Do you? Yeah, I mean, you have this image in your mind of this river over here, and you're supposed to be drawing a fence, and the fence has this river as one side of it. And then the other 3 sides are going to create the rectangular enclosure. So if I'm drawing it fairly well, it looks something like that. So we've got a rectangle. I'm only going to have fence along 3 sides of the rectangle, though, because it's beside a river, or a barn if you want. Now, there are 2 things that we don't know in this particular diagram right now without reading further into the problem. We don't know the length or the width, right? So we could call this piece X and this piece Y. Then what's going along on the bottom? It's also X, because that's what we know about rectangles, right? Rectangles have 2 sides the same, and they have the other 2 sides the same, but we only have one of the other 2 sides. Now, the question says, sorry, one more thing then. It says the enclosed area is equal to 1,800 feet squared. So the area equals 1,800 feet squared. All good? Okay, so we're just kind of piecing this together as we go. It wants us to find the minimum perimeter. What is perimeter? Okay, so perimeter in general, though, is what? Do you know how to think about it? Say again, Jamie? Like it's the distance around an object, right? The distance around an object. So on this object, Makai is right, we would actually take a look at the three sides and we would add them together, okay? So my perimeter is going to be equal to what? 2x plus y. And it tells us we want to find the minimum. The fact that it tells us we want to find a minimum is telling us that this is the derivative that this is the equation we're going to take the derivative of. But we're not ready to take the derivative of this equation yet because this equation has what in it? An x and a y, right? It has two things I don't know on one side of it. So step 3 over here says that I need to be able to write an equation in terms of only one variable. That is, looking at this 2x plus y, I need to either get rid of the x or get rid of the y. How am I going to do that? X and y are related in terms of the perimeter. How else are they related? The area. How can I, or what would be the equation of the area of this particular rectangle? Right. So this would be x times y, and it equals 1800. This is area, right? The area is x times y, the area is 1800, so these are equal to one another. So I can solve this equation, this portion of it anyway, for either x or y. It doesn't matter which one. So which one would you like to have this solved for? X? Okay. So x would equal what? 1800 over y. Which means that this value for x then gets put into the original equation that I was working with over here for perimeter. So I have 2 times 1800 over y, and then plus my y. How are we doing so far? This is actually everything you would have done in algebra. There's nothing yet that we haven't done in algebra. Okay? I can simplify this too. That's a little bit more algebra. How does this simplify? You might think in terms of how would I want to rewrite this so it's easy to take a derivative of it too. The 2 and the 1800 simplify first. What does that become? 3600. Thank you. I can write y to the negative 1 and then plus my y. This now I can take a derivative of. All right then, so we need a derivative of this, right? So what is the derivative of 3600 y to the negative 1 plus y? Negative 3600 y to the negative 2 plus 1. Good. Y in this equation is not like y in terms of x. That's not what's going on, right? This is just y. Just like a variable x would be. So you chose to use the y instead of the x. It's the same thing. What do I do next? What do I do once I take a derivative if I'm trying to maximize or minimize something? I set it equal to 0. Now, this particular one has a y to the negative 2 in it, so I'm going to rewrite this first of all as negative 3600 over y squared plus the 1 equals 0. Okay, is everybody good with that? Now what? Okay, we can do that. We can move the 1 over. It's one way to solve it. Then what? We can multiply both sides by y squared, or you can use that phrase cross multiply. So you're going to get negative 3600 on the left, and you're going to get negative y squared on the right. Then what? Yeah, the negatives can sort of cancel each other out because we can multiply or divide by negative 1. Then what? All right. So y would be equal to what? 60. And technically it's plus or minus 60, but it really isn't, right? Why not? We can't have a negative 60 because what is that y representing? a distance or a length, okay? In fact, it would be a good idea for us to come back over here and sort of make mention of the fact that there are some things that y can and can't be, and depending on how the problem's working out, it would be good to be aware of that. So in some cases, you are going to be aware of the fact that that's useful information, and sometimes it's just extra information that's not used. So in particular, if you take a look over here in terms of the y, what are the restraints or constraints, excuse me, on y? What values can y be? Obviously positive. You guys have already mentioned that. But it can't be just anything positive. What's the biggest that y could be in theory? 1800. Why 1800?
Because the area is 1800.
Yeah, the area is 1800, and to be honest, we should probably put restrictions, strict restrictions on this. Y really needs to be strictly between these two, right? Because if it's actually equal to 0, I can't get an area because I'd be multiplying by a length of 0. And if the y value were completely equal to 1800, then the x value would be 0, right? So the other piece, the other piece was x. In fact, I think I'm thinking about writing this like it was a perimeter. Hang on just a second. Let me take a step back. Technically, y could be bigger than 1800 because you could have the x value being like 1/2 or something. So we may not actually have an upper end on this particular one. If it were perimeter we knew something about, we would. But I don't think we actually have that upper end. Because if the x values were 1/2, we could end up, I mean, it'd be a very, very skinny garden. I don't know what we would do with it, but if you had an x value of 1/2, you could end up with a y value of 3600. So that would actually work. So I think actually do think that we only have that the y value has to be bigger than 0. Let me write that differently then. All right, so we'll write it in here. So y is greater than 0 and x is greater than 0. Let's just go with that for now. All right, sorry. All right, we have a little bit more information then. We believe that the y value should be 60, but our goal was to actually say that this is going to be a minimum perimeter, right? I need to make sure it really is going to give me a minimum and not a maximum, because just because the derivative is 0 doesn't mean it gives me a minimum, right? It might give me a maximum. So how do I figure out if this gives me a minimum versus a maximum? You have two options. Sign chart's one of the options. You said sign chart's one of the options. Did you have a different option? Number line. Yeah, number line is sign chart. Okay, we'll do that one since that's the one you guys thought of, but do you remember what the other option is? Second derivative. We could take a second derivative and evaluate our point of the second derivative. Okay, so you guys mentioned sign chart, so let's do that one. We'll have 60 here, and we need to test a point on either side of 60. So what's a number before 60 you guys would like to test? It can't be 0.
Can be 1.
It could be 1. Yes, I like 1. How about a number bigger than 60? 65? Okay. What are we testing these values into? The derivative, and you can do that in any particular location you'd like. One of the places for the derivative was up here. So if we'd like to do the derivative here, we can do it from here. So I don't have to go back to my other screen. So what happens if I put the number 1 in? I get a negative. Negative 3,600 over 1, and then plus my 1, so I get negative 3599. It's negative. What happens if I put the number 65 in? So put in 65 squared. Is it still negative? I hope it's positive. Double check it. So if we put in negative 3,600 over 65 squared and we add 1 to it. Did anybody actually test it? Grace is shaking her head. Did it work out positive? It is. Another way you can think about or realize that it's positive is remember that numerator was 60 squared. So when you have a numerator smaller than the denominator, then that fraction is going to be less than 1. So the second value, adding the 1 to it, is going to give us a value now bigger than 1. So negative and then positive means the graph goes down and then back up, right? So is it a minimum? Yes, and the sign chart's what's verifying that. So you have to show me the sign chart. Finding the slope being 0 is not sufficient to say that you found the minimum. You actually have to show that it really is a minimum. But we need to answer the question. It says find the minimum perimeter. Right now we found the y value. And then we also need to find the corresponding enclosure, the dimensions. So what am I going to find? If y is equal, we found y is equal to 60, what is x going to be? Let's start there. 1800 divided by 60. That's what y, or what x would be. So what is 1800 divided by 60? It is 30. So x is 30. And one of the things I'm supposed to find is perimeter. So what is the perimeter of this if x is 30 and y is 60? What is it? 120. You can think of it in terms of your picture if you'd like. You've got a 30 along the top, a 60 along the side, and a 30 along the bottom, and add them up. You can think of it in terms of your equation if you'd like. 2 times 30 plus 60. Right, that was the equation we had. We get 120. 120 what?
Feet squared.
Is it feet squared?
Or feet.
Feet on this one, yeah. Okay, so perimeter is in terms of linear measurement. It's feet. And I'm supposed to also then find the dimensions of the garden, or the enclosure anyway. 60 feet by 30 feet. So that's my answer. My answer needs to have units because the problem started out having units. Any question on that one? Okay. You would have gotten stuck in algebra if you had done this, and the reason you would have is because in algebra, this type of a situation, the ones you were always dealing with, ended up being parabolas that you were trying to maximize or minimize. And so you could do it by finding the vertex. Well, this equation that's squared in green is not a parabola, which means those methods from algebra don't work with this particular version of this kind of a problem. You had problems similar to this, but you wouldn't have been able to do this particular problem with the algebra concepts. You would have had to use a calculator and done some technology kind of things with it, and now you actually have some tools to be able to do that with calculus. Another one, this is a very common problem that you see given both in calculus and sometimes you'll see it talked about initially in algebra as well. We have a box with no top that we're going to build. We're going to do this by taking a 6 inch by 10 inch sheet of cardboard and cutting X inch squares out of the corners and folding up the sides. So can you picture what's happening? You're taking a piece of paper, cardboard, and you're cutting these squares out of the corners of it, and then you're going to fold things up on the sides to make a box. You're probably going to have to tape it when you're done. Okay? Now, what I'm going to draw is I'm going to draw a two-dimensional version of that, not the three-dimensional version, and we'll talk about the three-dimensional version as we sort of think through this. It wants us to figure out what value we should sort of cut out of those corners to make a box that holds the most stuff. Makes sense, right? Okay, so we're going to start by drawing a cardboard piece of paper. We're going to draw a rectangle. So we've got this rectangle, and we are going to cut out corners from the sides of the boxes. That's not going to work. Pretend my corners look really good. They don't.